Okay, so how do the human visual and cognitive system work? Okay, or in other words, how do humans decode a graph? Okay, so fortunately for us, there has been some excellent work in this area. The most important among them was this person called William Cleveland, who wrote a book on elements of graphing data. Okay, and what follows is what he has discovered. Okay, now Cleveland talks about 3 visual operations for pattern perception. Okay, so in any kind of visual problem solving, he says that we are doing 3 things. Okay, there is detection, there is assembly, and there is estimation. Okay, detection, assembly are very easy to understand. Estimation is where the most challenging visualization problem occurs. Right now, detection relates to completely understanding how our human eyes and brain works. It's about perceptual and cognition abilities. Okay, you know, the ideas of detection are not at all unfamiliar to you. As I explained to you, it will become clear. Assembly is nothing but graphic design 101. Okay, again, something that you guys are all familiar. So it's so much easier to tell. Okay, if I give this lecture to somebody, I have to dwell a lot more on what this assembly is. Right, it's about how to assemble graphic elements together so that it makes sense. And estimation is where the actual visualization happens, right? How do you now enable people to estimate things, right? Harder. Okay, let's go through each one of them in a little bit detail. So for detection, you need to have an eye. 70% of the body sense receptors reside in the eyes. Okay, so in a word, we experience world predominantly through our visual perception. Okay, although we have other senses such as hearing, touch, etc., but we know we make sense of the world through what we see. The eye and the visual cortex of the brain form a massively parallel processor that provides the highest bandwidth channel to human cognitive centers. It is important to understand how visual perception works in order to design effective visualizations. So the first thing is that eye is not a camera. Okay, a better metaphor for the eye would be that it is a dynamic ongoing construction project, right? So eye is very selective. Okay, but camera captures everything. Eye focuses different things at different times depending on where your attention is. Camera, everything is in focus. Okay, so attention is selective. There is a lot of that filtering that is happening. Okay, so there are things that you are seeing every day, day in and day out, and you will completely miss them because you have chosen to ignore it. Okay, your eye will ignore it. Camera, on the other hand, it has very good optics, single focus, white balance exposure. It's a full image capture. Eyes, relatively poor optics. It's constantly scanning, constantly adjusting focus between various depths. It's constantly adapting, and it is also actively constructing mentally a lot of information that is missing. Okay, so which is why we see things that are not in front of our eyes, and we can make out incomplete information and then complete the picture. So how does the eye detect information? Okay, our eyes see differences, not absolute values. Okay, and it is attracted to the edges, right? So when I look at the chair, this is a surface that is boring. Okay, it is uninteresting. Okay, the edges are where our interest lies, right? So we make out that this is some kind of a table for the chair because our eyes, and this is all happening pre-attentively. No, we are not thinking about it consciously at all, right? This is all very, very like a, how do you say it? I mean, we don't even realize it. So this is where our eyes are focusing. Okay, we make the shape. We know that this is a shear because we can detect the edges, right? So anything that is in between, which is continuous and the information does not change, okay, we lose attention to it. Okay, we kind of forget it. So what does it imply is that maximize contrast with the background if the outline shape is important, right? So if your outline shape is important, contrast becomes a very important factor. Visual system constructs surface color based largely on the color that is present at the edges, right? If we say that this is some kind of a purple, right? So essentially I am attributing the edge color to the rest of it. Okay. So if it changes very gradually, I will not notice it at all, okay, because I will attribute that this edge color applies to. But if it changes, right, dramatically in between to a different color, that also forms an edge, right, and therefore my attention will increase, my interest will pick up, and then I will start to detect it and then apply it to the following surface. So this is one color, right, and there is a edge, and then this is a different color, right. So what it says is that we attribute the color that we detect at the edge to the rest of the surface if the surface does not noticeably change, does not have other edges. We have a higher contrast sensitivity in the luminance rather than the chrominance channel. I think I mentioned this in yesterday. Okay, we are able to detect more subtle differences in the luminance channel rather than the chrominance channel. I will show you some example, will become clear. Our visual system corrects or misreads information based on perceived visual properties. Okay. Can you give me an example that we went through? Okay, so that doesn't misread, right? It still reads it as a circle. The area and volume thing, right? So if it is represented as a 3D shape, right, we will attribute something, and especially the perspective, the linear perspective example, the Ponzo effect. Remember the Ponzo effect, right? So the representation is a pseudo 3D linear perspective, right, on a 2D surface. And because we think that it is a perspective and we assign different values, we correct, right, we overcorrect the size of we misread the size of it. We will think that the one in the front is not actually big, but it appears to be big because it is in the front, right, because we do that mental adjustments. Okay. So this is the edge detection of the eye. Okay. So when you given these two surfaces, the first point of attention, okay, these are all studied through proper eye tracking devices. Our attention focuses on the center. So the luminance level, if you want to describe it, this is what it looks like. Lower luminance, and suddenly the luminance increases. This is this. Okay. So this is the actual representation of the luminance, right? But what we see is this. Okay. Like this, we see a spike here, and then it goes down like this. So this is the depiction of our attention. Okay. Our attention increases at this point, and then it goes back to the normal. Just because there is a higher luminance, we don't sustain the interest to a higher level, right? Our interest remains the same, right? It's just that it goes up and comes down. Okay. So now there are two rectangles that you can perceive, okay, with two different shades of gray. Okay. Which rectangle is darker? One on the left? Okay. Both are same?
It has gradient.
It has a gradient. Where is the gradient?
They both are same, sir.
I think the center line is making.
But why is the center line appears darker on the left than the right?
I think the center line has some gradient effect on the left.
Does the gradient go from 100 to 0 all the way?
It's just 5%.
Okay. So you guys are all like extremely sensitive to shades. Okay, probably the wrong audience. But most people, that I have shown this image, I have said that the left line is uniformly darker than the right one. Okay. Now, is the right one uniformly lighter, or is there a gradient there also? Okay, they're not so sensitive. Actually, whatever is happening on the left is also happening on the right. Okay. So I'll tell you what is happening. Okay. So the change is happening in this very narrow band, but we attribute it to the rest of the surface, right? And even the ones that are able to discern this difference, right, think that the darker part starts here and kind of goes all the way here, right, and the lighter part starts here, and like many people thought that this was one flat lighter color throughout, uniformly the same. Okay, so what is happening is there is a line at the edge, right, starts darker, tapers, and then reaches this color, and after that it is flat. Okay, same thing is happening here also. It is lighter, becomes darker, reaches a point, and then it is uniformly the same color. Okay, this is what is happening. So you said both are same, right? Yes. From here onwards and from here onwards, it's the same, right? What we see is that go here, it goes here, and then so this entire right hand side is attributed a lower luminance value than the entire left, right? So this is the perception. Okay, so this is a very famous diagram created by one of the Stanford professors. Is the squares A and B different or same? Okay, so if I draw a gray box that connects the both of them, you'll notice that they are the same, right? Even then people will see that there is a gradation in the rectangle that I drew to connect it, right? But it is not, it's a flat rectangle that I drew, because you still want to believe that A is darker than the B. I just resist thinking of A and B being the same. Okay, now why is that? Okay, shadow is one reason. Okay, so because B is in the shadow, okay, we think that it should be darker than what it is. Okay. Okay, it is light, right? It is light, and in the shadow.
Because it has a white base.
Yeah, correct, right? And also as a checker pattern, right? You will think that because B lies in that in the white ones, it is lighter. That's the first thing. Logically, it appears that B is white and A is black, and then the second thing is that it also falls in the shadow, right? So we kind of overread it, overcorrect it. Okay, Ponza illusion, we saw this, and it also depends on where the background, where this appears. Okay, so these two are same gray squares, but because they appear in the background of a darker or a lighter square, they colors also do the same thing to you. Basics of colors, you must have gone through it. So we saw this semantically resonant colors, and there is something called a Stroop effect. Okay. Now, Indu, can you tell me the colors? Don't read the words, but you have to tell me the colors. You just hold on. First, do it.
Green, red, blue, purple, blue, purple.
Okay. Now do the same thing with this. Color, you have to tell me the color, not read the word.
Purple, red.
It's harder, it takes substantially longer to read the colors of the second sentence as compared to the first sentence, right? Because of what is called as a Stroop effect, okay? So this is what is happening, right? The brain's ability to recognize the color of the word, since the brain reads words faster than it recognizes colors, okay? Colors recognition as opposed to reading a word requires more attention. Recognizing colors is not an automatic process. There is a hesitancy response, whereas the brain automatically understands the meaning of the words as a result of habitual reading. Okay, so there is this other effect called the pop-out effect. Okay, if you want to highlight something, we saw this example of how I highlighted the 5 by using a different color, right? It just pops out, right? And then pre-attentively you are able to process how many 5s are there in that entire string of digits, right? So if you want to use if you want to highlight something, some kind of an outlier, or emphasize something, in your data representation, we use something like what is called, in data visualization it is called pop out, but this is something that you already know, right? In order to create that dramatic emphasis that you do something, you create a visual variable that is very different from the rest of it. It can be using color, it can be using any of the visual attributes, right? It can be using shape, it can be even using motion, right? Everything is static, only one of them is moving, right? It could be identical objects visually, but then the fact that one is moving, the rest are not moving will attract attention. So this is, so the pop-up effect in visualization, for example, is here. Now these are the effectiveness of 3 antibiotics for a range of bacterial infection, okay? Now the ones on the left are the different bacteria. So, and then this is the 3 antibiotics. So you have penicillin, streptomycin and neomycin, and this is the amount of the medicine that is required to treat this particular. So this is very important for doctors, right? Once the test results come, you will have to figure out what is the antibiotic you want to administer, right? And typically you want to administer the lowest level that is required, the minimum that is required, right? So this one, kind of highlights and using. So the whole chart is a black and white or a grayscale. Only the one that you have to focus on is. So for a particular, for example, there are some. For example, this Proteus vulgaris, right? This and this are identical. Okay, this is the minimum, right? So therefore, both of them will work, but there are very clear preferences for the others, right? Neomycin is the most recent in terms of evolution. Okay, penicillin is the oldest and therefore less effective, but then neomycin is kind of covers most of the newer ones. But penicillin is still effective for 3 of those bacteria, like pneumonia and all that, and anthracis, pneumonia and all that. Okay, so how does this pop-out effect work? The larger the chromatic difference between the target symbols and the other symbol, it is easier to search. Okay, so you see in your color wheel, they are nearly opposite. Okay, so dramatically different. The chromatic difference is very high here, and therefore it pops out the best. Okay. Now in the same, when there is only one small color difference, only a smaller color difference from the target symbol, the search is difficult. Okay, so the orange and red are very close chromatically, and therefore the differentiation is much harder, right? So if you want to use colors to pop out, then you use the largest difference that you can possibly get. When there are many target symbols, the search is the most difficult. Okay. So again, this is obvious to us, but empirical studies have confirmed that this is to be the case. Right? You can figure out how far difference should be, what is the difference, and therefore when it becomes really harder to do. Okay. Now this is only if you with the foreground, right? Now combination with the background. For non-target symbols, if non-target symbols are similar to the background, then they are easy to exclude from the visual search, right? So you know what is happening here, So you kind of make the background closer to the non-target symbols, and therefore it's even more easier to ignore them, right? And therefore this one stands. Okay, there is a very good chromatic difference, and on top of that, the background is also helping you to de-emphasize the rest. A luminance difference plus a chromatic difference from other symbols and the backgrounds leads to the easiest search, right? So that one, it's still the background luminance is higher, okay, and that means that the target symbols are still visible and still non-ignorable, but then here their chromatic even the background is closer in terms of luminance level. So there is a chromatic similarity between the non-target symbols, and then there is also luminance similarity, right? So they are much more easier to exclude in the visual search. Okay, so the pop-out is the best in that case. A dark target on a light background with light non-target symbols can be as effective. So basically this is a variation of the second one, right? So whatever is happening with the background there with the darker chrominance, Here it's happening in the lighter case, right? Both the background and the chrominance level are of a lesser luminance, right? But then the target symbol is darker. So about as effective, the second and third, but the first one is also effective, but then this is even more effective. Okay, so we'll see an example of how this is applied in a visualization. Okay, so this is a map of water currents and temperature. Supports reasoning about currents in West and North Atlantic. The ocean current patterns are represented using streaklets, right? What you see as streaklets of different lengths and widths. Okay, now the length encode a data point and the width encode a data point, right? The background color provides information about water temperature. So you can see that it is a multivariate data, and that the width represents the velocity of the current. The length, I think the width and the length represents the velocity of the current. Anyway, I think we will find out. Find, for example, if you given a task such as find where the strongest currents are located. Okay. So what you are looking for is locations of fat long streaklets. Okay. Find out where something that was dropped in the water, for example fish larvae, might end up after a period of time. Okay. So find where particular train of streaklets lead, okay, because it can tell you where it might have ended up. Find regions with the coldest water. Find locations that have the darkest blue color. Okay. So in the regions where the current velocity is low, thin lines, the direction is unclear. Okay. So this is a kind of a critique on the solution, right? So when the width is higher, the direction is obvious, right? Because it has got a fat head and a thin tail, right? But if the current velocity is slow, then the width reduces, and so that it is just the very little difference between the head and the tail, and therefore the directionality becomes unclear. Okay, so that is a point here that you'll have to figure out, right? So despite all this interesting encoding, that it could potentially have problems such as this.